Hello. Hello, Mr. Eric, Mr. Ryan. How are you today?
Good.
Okay, good. Okay, so today we talk about an interesting problem. It's called integer break or split product. So basically, given an integer like 7, yeah.
I'll give one.
7. So
No, I'm not.
So we want to split it like 7. How many ways you can split it? You can split it. You can say 1 plus 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 1. Right? 7 ones, yeah. 2, 4, 6, 7. So the product, you multiply all the 1 together. You give you the 1, right? Okay. You can do it as 2s. 2 plus 2 plus 2 plus 1. And if you multiply all these numbers together, you give me the what?
It'll give me
What? What can we get? Multiply.
9. No, wait.
Multiply. 8. Come on, yes. And or you can do it in 3 and 3 and 1. That will give you
9.
Okay, so any other ways? Yeah, of course. Look, you can do this 2 plus 4 plus 1, right? Yeah? That will give me 8, right?
Yeah.
Or 3 plus 4. That will give me 12, right?
12.
Yeah?
Yeah.
So this is the optimal. We want to maximize. We want to maximize the product by breaking the integer, right? Look, any other ways we can do it?
I don't think any are bigger than that.
How about 3 plus 2 plus 2? That's also 12, right?
Yeah.
Yeah. This is also okay. Yeah. And yeah. How about what? How about what?
They get the golden medal.
How about 2 and 5? 2 and 5, that give me 10, right? This is another way, right? Right? Yeah? Alright?
Yeah.
Okay, so let's try another example, right? Let's try another example. Remember, this is optimum, right? Just remember, okay? Let's try another example like 5.
I'll give you
5.
11. No, I'll give you. Yeah, I don't know.
Okay, 5, Eric. Obviously, you split into all ones. It's not optimal because the product is 1, right? So we skip that. 2 plus 3, that will give me 6. 2 plus 2 plus 1, that will give me 4. What? Another one. What? 3 plus 2, give me 6. 3 plus 2 plus 3 is the same. Yeah? How about 4 plus 1? Give me 4. Okay? Alright?
So this and this.
Yeah, so any idea how we're doing this?
We're using 3s.
Well done, that's a good observation. Yes, the 3. It's optimum to split into 3s. Look, because look, if 5, right? If it's 5, we can split into 2 and 3, which is the optimum, right? Because 3 is preferred, right? And then the 7, we split into 3 and then 4, right?
And 3 and 3.
Until, look, this 3 and 4, because this 4, so we can give a 3 until the remainder is less or equal than 4, right? That will give the optimum, right? Can we try to write this problem? Yeah?
Maybe we can.
Maybe we can't. Okay. Define.
Definitely can.
Define.
And definitely can't.
Split product.
Ooh.
N. Okay. If n equals 1. Okay. By the way, the integer we're looking at is the positive. Okay. Not yet. Or n equals 2. So what should we return? If n equals 1 or n equals 2, how many ways can you
1.
1, yeah, because there's 1 is, you can't split it, you can just split it as 1, right? 1 or 2, right? 2 is 1, right? Okay, then look, there's another special case equals 2. What should we return?
1. 3.
Oh, no, 3, actually 3, because 2 is here. 3, 2, 2, yeah, because 1 and 2, right? Yeah?
Yeah.
And
2 and 1.
Yeah, or 1 and 1. But 1 and 1.
3 or 0.
1 and 1 and 1, they will give me the product 1, which is smaller than 2, right?
Yeah.
So return 2.
Still
Right?
makes a difference.
Okay, so now let's store this answer, the maximum product. beginning 1. While n is bigger than 4, okay? Then we times, look, if n is bigger,
What if it is 4?
sorry?
What if it is 4?
What is 4?
And is
Oh,
4.
it's 4. Okay, that's a good question. N is 4, then it's 4.
Well,
Look, if n is 4, what can you split?
2, 2.
2 and 2, right? You give me the 4, right?
Give me a 4.
Yeah, alright? Alright, does it make sense?
Of course.
Because if you split into 3 and 1, that's not optimum, right? So 4 is about separation between, because it got a separation. If it is more than 4, we can times equals 3, and then we take 1, 3 out, right? Right? Alright? For example, 4. 4, look, 4, let's look at the 5. 5 equals 3 and 2, right? Right? Yes?
Yeah.
So I take a 3. Now I have 1, 3. And then now n is 2. So what should we do? Return what? Answer. Answer is 3 times remain times n, right? Does it make sense? Alright? Does it make sense? We can take a 3. If it's more than 4, we take a 3. Right?
Yeah.
And when this while loop exits, the n is smaller or equal to 4, right?
Yeah.
Now we just multiply the remainder, right?
Yeah.
What's the time complexity?
Oh.
Oh what?
Mm.
What oh what? Look, what's this? How many iterations maximum?
N.
Oh n, yeah. Because look, every time we're taking 3, so the loop will be n divided by 3. But look, Eric, n divided by 3. But we drop the constant, right? We drop the constant, so it's n, right? Does it make sense?
Yeah.
Okay. That's it. That's it. So listen up. So okay, so what's here? What's here? Okay. Okay, good job. Can you tell me what does it mean?
I mean, subtract 3.
Yeah. See, the ultimate is allocate in 3 groups until the remainder is less or equal than 4, right?
Yeah.
Yes? Okay.
Bye.
Not yet. This is one part of it. We can also solve this problem by
Oh,
By what?
smiley face, cash.
by what? Oh yeah, it's something to do. Yeah, remember a few
Mimo.
memoization, dynamic programming. Yeah.
Yeah.
Eric, look. So let's say Fn is the maximum product that we can get by splitting the integer n, right? Don't come on. You're making people dizzy, okay? Yeah. Okay, does it make sense? Yeah.
Yeah.
Okay, so if n is 1 or n equals 2, then we know return the 1, right? Right?
Yeah.
Okay. So now the thing is, how can we split this? Okay, so is it equals to I don't know, because how many ways I can split into this? Can I, for example, like I can try with 1 and then fn minus 1, right? Yeah? Alright?
Yeah.
Look, if I split it 1 and then I can do another fn minus 1, or it could be, if I don't want to split these, I can do this 1 and n minus 1, right? Right? Does it make sense?
Yeah.
But this 1 can be between 1 to n minus 1, right? Does it make sense?
Yeah.
Because look, f5, I want to split this integer 5, right?
Yeah.
So I can make it as 1 and 4, right? And 2 and 3, right? Yeah? And 3 and 2, 4 and 1, right? So this I can go from 1 to 4. And this is n minus I, right? Right? For each one, Eric, look, for each one, I can choose to split it, which is fn minus I, right? Or I decide not to split it, I just use the integer, right? Does it make sense?
Yeah.
So look, so fn is the maximum of what? Let's do this I, okay? For I times n minus I, yeah? I just said if
After
Eric, if
Yeah.
I just split this integer between I and n minus I, right?
Yeah.
Or I, what?
Something.
F n minus I, yeah? If I split the integer I, but I don't want to split it, I will keep splitting it, right? And where I is between 1 to n minus 1, right? Does it make sense?
Mm-hmm.
This is called dynamic transition function. Does it make, yeah, do you still remember?
One.
Transition function. Does it make sense? So can you explain to me? Come on.
So
Yeah?
this bit.
Yeah. So what I'm just talking about, yes. Explain to the people all over the world, okay? So,
Okay.
So yeah. Come on.
So you can see us. So it's the Fn
Yeah?
can be the maximum of the I and times the
Yeah, I know. So what's this bit? And what's this bit? So look, F5. So I want to split integer 5, right? Yeah? So let's say I will be between 1, 2, 3, 4, right?
One,
Alright.
two,
So
four.
you will be two choice. I can split 1 and then 4, right? 2 and 3. 3 and 2. 4 and 1, right?
Hmm?
This is this bit. I times it together. Or I keep splitting this. This will become F4 problem. That will be 2 and 2. Or does it make sense?
Yeah.
Yeah?
Yeah.
Which one, you tell me which one is continuing splitting this function? The sub problem. Because dynamic problem. Yeah, because look, you have F. Okay, don't wrap it out, okay?
Why? Maybe it's a bit too late.
Okay. So look, we are given this function and with determinate condition. Now we can implement it using how many approaches?
And
How many dynamic programmings are we talking about? Remembering?
two.
Okay, what are those?
Top
Down and the other one?
bottom
Bottom up.
up.
Okay, top down and bottom up. Okay, so which one is the recursion with minimization?
Oh, top D T D.
Top down. Yeah, top down. Okay, so look, let's do it. Define
Okay.
Fn column, yeah. And then
Not
we
really.
look if n is 1 or n
N.
equals 2, return what?
Return one.
Well done. Okay. And now look at let's say this answer. Let's say a answer equals 1. Okay. Look, for I in range what? Can you tell me what range what? Range what? The I, remember the I. How many ways that we can split it between? Alright. So I will be from what?
1
1 to what?
N.
N, yeah. So actually it's 1 to n minus 1, but you're given the 1 plus 1, yeah? The second thing over. And then look, answer will be equal the maximum of what? I times n minus I, right?
Yeah.
Or I times f n minus I, right? This means we keep splitting it, right? And then, yeah?
N minus I.
Yeah?
Yeah.
And return what?
Answer. Of course.
What's missing here?
Cash.
Cash, yeah, we are done. Cash. Yeah, because if you're not using the cash, what happens? You'll be exponential. Yeah, we are calculating over and over again. We want to avoid computing the same thing over and over again. What's the time complexity? Think about it.
No cash.
No cash. What's the time complexity? Right, Eric?
Beep, 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 beep.
What you doing?
Nothing.
What you doing?
Nothing.
Come on. What's the time complexity? What's the time complexity?
The time complexity is
What?
O, O,
What?
O, O,
What?
O,
Alright?
O.
It's actually O(n) squared because look, it's
That's really.
alright. Look, because we are having a 4 and then here, this is because we're calling it, right? What's the space complexity?
One.
what?
Something.
What? How many values of n, fn we are calculating? How many maximum items can be stored in the cache? What? What? Eric?
1.
Why is O1? We're using the cache. Come on. How is that O1?
N.
O1. Come on. Because we are calculating, we need to store the numbers in the result of fn values in the cache, right?
Yeah.
And then it will be f1, f2, f3 until fn. So that's the complexity, the space complexity is O(n), right? Come on, Eric, Ryan. Why this is O(n), but here we are calculating another, right? So that will be O(n) squared, right?
Yeah.
Okay, come on.
This complexity.
This is top down.
N squared.
Top down. Dynamic programming, which is usually implemented using recursion and memorization. Okay, let's write this down with another approach. Listen up. I'm going to
Play.
listen up. Okay, so now look in the bottom-up approach. What's the first value we need to calculate? What's the difference between top-down and bottom-up?
Top down is we remember. Memorization.
Yeah, so I'm saying this top down because we want to know the fn value, right? In order to calculate fn value, we need to expand it fn minus 1, fn minus 2, right? Right? Etc. Using this direction into f1, right? This is called top down. But in the bottom up,
You start from the bottom.
so which is you are constructing the values from f1, f2, and then you go in this way. This is called bottom up, right?
Yeah.
Does it make sense? Okay, so now with the bottom up, we usually don't need to use the recursion. We use the array, right, to store the values, right? Yeah.
Yeah.
So let's do it. Define fn, and then look. Let's have a dp array, right? dp array equals at the beginning it will be 1 times n minus 1, right? n plus 1. Okay, now look, we want to start from I in range. Let's do this 1 to n plus 1, right? This is the first iteration is the fn we are now calculating, and second iteration is to list the number of different ways to split the integer, right? Alright, so for j in range, okay, what's the two values here? How many ways we are splitting the integer? J in range what? You just give me the answer, it's the same. What's the answer?
1.
1 and what? What's the second?
N.
There's no n. I'm just saying I plus 1. No, it's I, yeah, it's not plus 1 because we're splitting 1 to I minus 1, right? We are going to with the I minus 1. Okay, so now dpi, right? Because I'm calculating this.
Equals.
This is dpi we are calculating equals max of dpi. Yeah, we're storing the maximum, and then look. J times there's no n. I minus j, right?
Yeah.
Or j times what?
dp.
dp what? I what?
Minus
j. Yeah. You see, this is quite similar than previous one, right?
Return.
Yeah.
Return.
Eric, does it make sense? Return which value?
dp.
dp which value?
Minus 1.
Minus 1. Minus 1 is which value?
It's the
Which value is the minus 1?
last one.
Last one. And which is the last one? dpn. dpn, yeah?
Yeah.
Yeah, okay, dpn, yeah. Because this is n plus 1 is actually dp0 to dpn, right? Right? Does it make sense? So your last one is dpn, is the value we're looking for.
What's the time complexity?
Look, yeah, the time complexity for this one is quite easy, yeah?
Complexity.
It's just quite easy to see, yeah? Straightforward, yeah? What's the time complexity? What? This is n iteration, and this one is from
n squared.
yeah, n squared. What's the space complexity?
Uh,
We are using a DP array,
n.
and because it's look n size, yeah. Does it make sense? Look, Eric, look. This is quite similar to the top-down dynamic programming, yeah. If you remember, Eric, yeah. Yeah, look at this one. If you choose to split with j and I minus j, two numbers, or if you choose to split it with j and continue splitting with I minus j, this integer, right?
Yeah.
Does it make sense?
Yeah.
Okay, so and last we return the last one. Look, this is more straightforward and more simple to implement, right?
Yeah.
And it does not have a recursion. Usually it's faster because the recursion contains the functional calls. Yeah, because the computer will call the function and there's an overhead. But this one is just the array, and we're just iterating the array just to update the value, so it's usually faster. Does it make sense? Yeah. Which one is the fastest? 3 ways. Greedy. The first one, mathematics greedy, split into 3. Do you still remember? The second one, top down, and the third one, bottom up. Which one is greedy? Yeah. Do you still remember the greedy? The complexity.
Greedy.
The complexity.
And
O n, yeah.
about 2 days ago.
O n, yeah.
Yeah.
So which one is faster? O n or O n square?
O-N.
Well done. That's what I want. Yes.
O-N cubic is slower than O-N squared.
Well done. Well done, Eric. Ryan.
O-N.
Okay, that's it for today. So you can say bye bye and see you tomorrow.
Bye. Bye.
Bye bye. Bye bye.